Hello and welcome to Lecture 6 in Equilibrium Chemistry. As promised, I'm giving you the second half of the Bronsted-Lowry acid-base theory today. It deals with predicting Bronsted-Lowry systems. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis upon which the diploma exam is set, and hopefully you're referring back to this page from time to time to get a sense of how your mastery of the material is coming. Bronsted-Lowry theory has its shortcomings. Most importantly, it does nothing to explain why some acids are strong and why some are weak, why some give up their protons readily and others hang on to them. We have to rely on experimental evidence to determine what will happen in every given system. And as a result, after we've run those experiments, we use a table of relative strengths of acids and bases to predict other Bronsted-Lowry systems. And there's one such table in your data booklet, and I'm going to show you a snippet of it on my next page. The theory assumes that all acids and bases in the system react by either donating or receiving protons, but that the only reaction that will occur to any significant degree is the net reaction of the strongest acid donating a single proton to the strongest base. And we predict Bronsted-Lowry reactions using a set of rules to determine what's present in solution and a 5-step method. So I'm going to present you with the rules initially and then describe the 5-step method, which will harken back to the work we did in the redox unit. So these are the rules for determining what's present in the system. If we have an ionic compound in water, then we have free ions in solution. So for calcium hydrogen carbonate, we're going to have the calcium ion, the hydrogen carbonate ion, and water. For ionic hydroxides, ionic oxides, such as sodium oxide and calcium oxide, we're going to have hydroxide and the cation. So for the sodium oxide, we're going to have the sodium ion and the hydroxide ion. For the calcium oxide, we're going to have the calcium ion and the hydroxide ion. For strong acids, such as hydrochloric acid or nitric acid, we're going to have the hydronium ion present and the anion attached to the acid. So for hydrogen chloride, we're going to have the hydronium ion and the chloride ion. For nitric acid, we're going to have hydronium ion and the nitrate ion. For weak acids, we're going to assume that they're in the solution as presented in the question. So hydrogen fluoride is in the water as hydrogen fluoride. The hydrogen sulfate ion exists in the water as the hydrogen sulfate ion. And finally, for weak bases, such as ammonia or the hydrogen carbonate ion, they exist in solution as presented in the question. So in this case, the ammonia exists as ammonia, and the hydrogen carbonate ion exists as the hydrogen carbonate ion. You're going to have this table handy to analyze these questions as you go through them. So our 5-step method then, to determining the Bronsted-Lowry reaction, the first step is to list all entities present in the system. And this is the piece that requires the table that we just went through. Then you label all Bronsted-Lowry acids and all Bronsted-Lowry bases. And you do this by referring not to the table that I just reviewed, but to the table of acids and bases found in your data booklet. And we'll have a look at that in a minute. Then you identify the strongest acid and the strongest base. And the strongest acid will be found at the highest point on the left-hand side of the table. The strongest base will be found at the lowest point on the right-hand side of the table. Then you write the reaction that involves a single proton transferred from the strongest acid to the strongest base. And then you use a left-hand, right-hand rule to see if reactants are favored in the system or products are favored. In the redox unit, we can actually determine whether or not a reaction will be spontaneous or no reaction will occur at all. Here we can simply determine whether or not there'll be more products in the system at the end of the day or more reactants. And here's the snippet of the relative strengths of acids and bases table I promised you. The left-hand side lists the acids, and the right-hand side lists their conjugate bases. And you'll see the difference between the two is a single proton in every case. There's a column for Kc, and you'll notice that for acids, it's referred to as a Ka value. And we'll deal with this column in my next lecture. And you'll notice that there's a grade in acid-base conjugate pair here, hydronium and water. The 6 acids listed above hydronium on the left are all extremely strong. they have what's described as a very large Kc value, so large that we can't even determine its value. That means there's very, very little reactant left when you mix these with water. And when you're dealing with one of these acids, we assume, because it's reacted with water, that hydronium is in fact the strongest acidic species in the system. And then as we go down the left, we're dealing with ever increasingly weaker acids. However, as we get on the right, we're dealing with ever increasingly stronger bases. Up at the top right here, we've got the 6 conjugate bases for the 6 strong acids. And they're extremely weak bases. They're much weaker than water. So if any of these are in a Bronsted-Lowry system that's in an aqueous environment, we assume that the water is the strongest base. And just to repeat the rules as I set out a couple of slides ago, for aqueous solutions, the hydronium ion is the strongest acid, while the hydroxide ion will be the strongest base. The latter is seen in reactions of ionic oxides and ionic hydroxides, such as sodium oxide or sodium hydroxide. And again, this is straight out of the table as I just described it a couple of slides ago. Nothing can act as a base in water if it's a weaker base than water. So this is referring to the 6 conjugate bases to those 6 strong acids up in the top left. Therefore, therefore the conjugate bases of the 6 strong acids are not considered to be bases in aqueous environment, since they're all weaker than water in basicity. They're bases, but they're too weak to be involved in the Bronsted-Lowry reaction. And in doing these problems, we assume that each reaction involves the transfer of a single proton from the strongest acid to the strongest base, and that the 2 reacting species are present in roughly similar concentrations. So let's look at an example. Reaction between aqueous drain cleaner and ethanoic acid. So our first step is to list all species present. Sodium hydroxide is an ionic hydroxide. Under the rules presented, we list the cation and hydroxide. Ethanoic acid is not one of the 6 strong acids, so therefore we write it as presented in the question, and the entire system is in an aqueous environment, so water is present. Step 2 is to identify all acids and all bases, and here we've done that. Hydroxide is a base, ethanoic acid is an acid, water is an acid and a base. And you'll see that water is listed on both the left and right hand side of the acid-base table. Step 3, identify the strongest base and the strongest acid. Strongest base is hydroxide, strongest acid is acetic acid, ethanoic acid. Write a Bronsted-Lowry equation whereby the strongest acid, in this case the ethanoic acid, transfers a single proton to the strongest base, in this case hydroxide, to form the ethanoate ion and water. And then do a left-hand, right-hand analysis on the table of relative strengths of acids and bases to determine whether or not you're going to have more products in the system at the end of the day or more reactants. And that looks like this. And if you put your left hand on acetic acid and your right hand on the hydroxide ion, you'll see that your left hand is higher. So protons will flow readily, and in point of fact, this system will favor products. So the bulk of this system will exist as ethanoate ions in water. It's said to be product favored. Let's look at one more. Ammonium nitrate fertilizer is produced by the quantitative reaction of aqueous ammonia with nitric acid. Write a balanced acid-base equilibrium equation and predict where it lies. All right. So the first step then is to list all products, all materials present. Ammonia is a weak base, so we write it as given to us in the question. Nitric acid is one of the 6 strong acids, and the rule there is we list hydronium ion and the nitrate ion. And of course, it's in an aqueous environment, so water is present. Identify all acids and bases. Hydronium is an acid. The nitrate ion is a base. It's weaker than water, but it is in fact a base, so let's identify it as such. Ammonia is a stronger base, and water is a base as well. In fact, water is both an acid and a base. We identify both the strongest acid and the strongest base. Hydronium is the strongest acid. Ammonia is the strongest base. We write a Bronsted-Lowry reaction where the strongest acid, the hydronium, transfers a single proton to the ammonia. to generate the ammonium ion and water. Step 5 then is to do a left-hand, right-hand analysis to determine whether or not products or reactants are favored in the system. So we put our left hand on the hydronium ion on the left-hand side of the data booklet page. We put our right hand on the ammonia found on the right-hand side of the data booklet page, and we see that our left hand is higher. Therefore, protons will flow from the hydronium to the ammonia, and in point of fact, products again will be favored here. So the bulk of this system will exist as ammonium ions in solution. I think I've got one more that I'll let you work out on your own. It's the classic primary school volcano, vinegar, and baking soda. They want you to determine the predominant reaction between the Bronsted-Lowry acid and base, and whether or not products or reactants are favored. And you should pause the video because the answer to the question is as follows. I refer you to any homework your teacher assigns in this matter. I hope you found this video of some value. We'll see you next time when we do some heavier mathematics, dealing with Ka and Kb calculations. Thank you very much.